What's up, guys? We're going to keep moving along in Chapter 4. So today we're looking at Section 3, which has to deal with nonlinear functions. A nonlinear function is a function whose graph is not a line or a part of a line. A line in math, by the way, is something that is a straight line, because I know a lot of you, you would look at something, whoops, things going crazy here. You would look at something like that and say, well, that's a line, but in math, we don't consider that a line unless it is a straight line. So those are not lines. I know that's not perfect, but that's close enough. This is a line. Okay. A linear function is a function whose graph is a non-vertical line or part of a non-vertical line. So you can see here that this is linear because it makes a straight line. This is linear because those would fall on a straight line. That's linear because it's a straight line. Nonlinear is a function whose graph is not a line or a part of a line, like this shape right here, which we'll spend a lot of time on later in the year. This one, which you'll see in Algebra 2 a lot. And then this right here, which is a discrete absolute value function, which we'll look at those as well. So these don't set on a straight line. Make sure that you have this copied down, the difference between a linear function and a nonlinear function. We're going to be focusing on these linear functions a lot over the next few weeks. But here is just a moment of truth. The end of autumn, 45 degrees, in the beginning of spring. Man, it's just too hot or too cold. One or the other. Classifying functions, the area A in square inches of a pizza is a function of its radius R in inches. The cost C in dollars of the sauce for a pizza is a function of the weight W in ounces of sauce used. Graph these functions shown by the tables below. I'll get to that in just a second. Is each function linear or nonlinear? All right, so I don't have graph paper on here. I would encourage you to do this on graph paper. But what this is getting at is if I were to graph these, and let's say I can't get the thing in the way. I'll put a 2 there and a 4 there. And 6, 8, and 10. All right, so there's those. I'm going to put a little break, and I have, we'll start with, well, actually, I don't need the break. Ignore that break. We'll say that's 10, 20. That's not going to be big enough. Time out, people. Let's try this again. All right, so here we have our graph, and I need to look here and see that I need to go up by a lot more, so let's go by 50s. How about that? So 50, 100, 150, 200, 250, 300. And hopefully on your graph paper you're doing this a lot cleaner. It's hard to do that on here. So here I have a radius of 2. That first dot would be somewhere in this area. When the radius is 4, the area is somewhere closer to 50. When the radius is 6, the area is up here around 113. When it's 8, it's closer to 200. And when it's 10, it's way up here. And you kind of start seeing how this has a curve to it. All right, and on graph paper, if you did it nice and neat, it'd be a lot more prevalent. But this is a non-linear function. And you could tell because it's not straight. Now, if I come over here and I graph this one, all right, the weight, the sauce is cost compared to its weight. So I have 2, 4, 6, 8, and 10. And here we could say, let's go by dollar increments. So 1, 2, 3, 4. All right, so 2 ounces of sauce is going to cost 80 cents, which is just a little bit below 1. 4 is $1.60. 6 is going to be $2.40, which is right around in that area. 8 is $3.20. And 10 is going to be $4. You can see on this one that this creates kind of a straight line. And again, if you did this on graph paper, it'd be a lot clearer. So this is a linear function because when graphed it makes a line. I think that's really straightforward. I don't think you'll have any issues with that. Let's take a look at this. Table shows the total number of blocks in each figure below as a function of the number of blocks on one edge. So here's what this means. Number of blocks on one edge. So this is an edge. There's one block. Total number of blocks is 1. The ordered pair would be 1, 1. This has 2 blocks along the edge. So 1, 2 makes up 8 blocks for an ordered pair of 2, 8. This has 3 blocks on the edge, 1, 2, 3. There's 27 blocks in here, 3 times 3 times 3, and the ordered pair would be 3, 27. So that's what we're looking at. It says, what is the pattern you can complete to use the table, represent the relationship using words, an equation, and a graph? Well, I kind of just got to it a little bit. You notice here that this is going to be 1 times 1 times 1. This is 2 times 2 times 2. This one is 3 times 3 times 3. All right, so each time, what is it? It is this particular number cubed. So I'm not going to draw it, but what I would do is I would take, I'd say the number of edges cubed, that's the words. The equation is going to be y equals x cubed, and that's how you'd write that. And then we'll draw the graph in just a second. Let's go ahead and fill in these other values. So 4 times 4 times 4 is 64 for an ordered pair of 4, 64. This would be 5 times 5 times 5 is 125 for an ordered pair of 5, 125. And I know that yellow is kind of difficult to see there. If I graph this, all right, and this is the number of blocks on the edge. So I have 1, 2, 3, 4, and 5. And here I'm going to increase by, let's see, I go to 125. Let's go up by 25s. So we'll say 25, 50, 75, 100, 125, 150. You'll see something that happens here. So I have 1, 1, which is going to be way down here. Then I have 2, 8, which is still going to be pretty low. Then I have 3, 27. It's going to be just a little bit above that 25. 464, all of a sudden we start making some pretty big jumps here. And then by the time I get to this 5, it's 5, 125, which is going to be somewhere up here. You start seeing this shape, and we did that activity the other day where we were looking at pictures of graph. This is an exponential function, all right? So this is going up, 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 and it just gets steeper and steeper and steeper, but it never actually gets truly vertical. But it does look really, really close to being vertical. So that's the way that that would graph. There's your equation. Again, the words would be the number of edges cubed. All right, so writing a rule to describe a nonlinear function. My first suggestion would be to go ahead and write these ordered pairs as an XY table. So I have 1, 2, and then 2, and 4, and 3, 8, 4, 16, 5, 32. And what you're interested in, if you're going to write a rule that represents the function, is you're interested in a couple relationships. First of all, you want to look at how these increase. So this is increasing by 1 every time, plus 1, plus 1, plus 1. So that's a good thing. Then I also want to look how these change as I go from here to here. This is going to give you some hints as to what may be happening here. But when you're talking about a function, remember, you're talking about an input and an output. So the most important relationship that you're looking for is, what do I do to this number to make it this? And what do I do to this number to make it this? And is there something that I could do to this number and get this on every single one of these instances? What can I do with 1 that gets 2, that I do the same thing to 2 and get 4, that I do the same thing to 3 and get 8, and so on? So this relationship is the most important. But these side relationships as I go down can give us some clues here. So let's take a look at what happens. How do I get from 2 to 4 and then 4 to 8? Well, hopefully you see that that is being multiplied by 2. So here we go. We have something that's being multiplied by 2. And whenever that happens, when you have repetitive multiplication, that means there's an exponential function that's happening here. Okay, and usually whatever this number is that's being multiplied, that's going to be your base for that exponential function. So 2 is going to be my base, and what I'm doing is I'm looking at the powers of 2. So just 1 2, or 2 times nothing, 2 times 1 is 2. Here I'd have 2 times 2. This tells you how many times 2 is a factor. So 2 is a factor once. Then to get to here I have 2 times 2. 2 is a factor twice. To get to this one, it's 2 times 2 times 2 is 3 times. To get to this one, it's 2 times 2 times 2 times 2. 2 is a factor 4 times. This one, I have 2 times 2 times 2 times 2 times 2. There's 5 2's. So you see that this is going to be a factor. This is the number of times 2 is a factor. So this becomes the exponent. If you remember, exponents tells you how many times a number is a factor unto itself. So the rule for this function, this is kind of difficult. So if you don't see this right away, don't get too frustrated. But this is the rule for this function. And you can kind of see that because this is being multiplied by a repetitive value. Generally speaking, that means you're going to have a variable in the exponent. You're going to have an exponential function here. And that's that. We'll look at more problems like this in class. Don't get too frustrated if you're a little bit confused on it. And I believe that's it for this one. Yep, that's it. So hopefully you took good notes. I'll see you in class.